This is really hard to answer right now. When the transistor was invented a couple of decades back, nobody really knew this eventually will evolve into something like smartphones or, I don't know, the internet and things like that, YouTube, TikTok, and so on and so forth. And I think with quantum computing, it's very similar. Quantum computing has the potential to solve really hard optimization problems, for example, and that eventually may lead to better drugs for, curing diseases or for more efficient, I don't know, chemical processes to run our future vehicles in a more efficient fashion or to predict the weather better. So it's really hard to tell, but what quantum computing does, it solves really hard problems in a variety of domains, and if we manage to make that work, it's definitely going to have a substantial impact into our daily life.
So any industry that has to deal with materials at the end of the day, be it the development of novel materials for building new solar cells, or for example developing new drugs. So anything that the basic or the fundamental level is quantum mechanical, I think can be heavily impacted by quantum technologies.
I think the impact the daily life of all this quantum technology will be very indirectly. So you can see it as and it works different for each of these technology. Concerning quantum sensing, you can use it for, let's say, in the healthcare industry, for detecting cancer in the future. For the quantum computing, you can use it for developing new materials, new pharmaceuticals, new chemical stuff. And what is also of important is the topic of safety and security, which is concerning to all this quantum cryptography, post-quantum cryptography, and also this quantum key distribution.
Yeah, that I think is going to be a lot quicker. If I think that ultimately the impact on computational biology and material discovery is going to be the day-to-day impact, the biggest day-to-day impact, then I think way before then, in fact, I think within the next 6 to 12 months, things in cybersecurity will be impacted very profoundly. The reason I say that is in cybersecurity, you have locks and you have keys to open the locks. And keys are currently deterministic, they're algorithmic. Every key is algorithmic. So I think that over the course of this next 6 months to 12 months, keys that are seeded from randomness that is extracted from nature, so this is things that can be tested with a Bell test, these will be commonly available. And this will happen in the next 6 to 12 months.
The milestones for each quantum technology are very different, I think. For quantum sensing, for instance, you have the sensing, so the next steps will be the technology steps. This means miniaturization, high integrations, and cost reduction. And then you have a fixed sensor where we can find application in the field, and we come up from use cases to business case, which is very comfortable for companies. For the milestones for quantum computing are much larger, I think beyond the 10 years, that we have a performance of the quantum computing chips and all these qubits, where we can make a really impact on development of material, simulation, optimization, and all the stuff. But close in front of the door is the safety and security theme concerning this quantum cryptography, and because it lasts some years to make it comfortable to the industry, we should start now to be secure in the future.
Yeah, so it's difficult to say because it has to do both with the development of applications and algorithms as well as with hardware. But I'm going to take an optimistic stance and say 7 to 10 years.
It's a big topic, and it's a topic that has been well understood for some time, but it's only now in the last, I would say, year that we're getting to the point that we can do something about it. There are 3 things that I'm really looking at. One of them we've been working on now for 6 years, which is materials for carbon sequestration. So how do you sequester carbon safely in our environment and sustainably? It has an incredible impact on the world as we know it. as you can see, I'm very passionate about this. So I think this will happen. I think the impact on hydrogen fuel cells and lithium-ion batteries and sort of basically material discovery, either storage or generation, is very, very close second. So we have alternative ways of powering our everyday lives. And then I think there's the sort of the holy grail, things like nitrogen fixation and things like photovoltaic cells, which can be far more effective. And I think in each area there are different types of research which now suggest that we're getting closer. If somebody asks me how close, I think if we have logical qubits that were perhaps with error suppression rates of 10 to the minus 10 or better, I think we get there with maybe, I don't know, 500 or 1,000 logical qubits, possibly 1,000 logical qubits. We start to make a real impact on these areas.
One could actually argue that currently quantum computing is actually contributing to global warming, right? Because you have machines working on 0 Kelvin, and in order to get it to 0 Kelvin, you have to invest a lot of energy to get it there. So technically, I've even been in discussions about like, is actually, quantum computing harming the environment right now? And of course, this is one rather pessimistic way of looking at things. And as a counter argument, you could make the point like, okay, with quantum computing, we can improve chemical processes. Maybe we can do, better climate simulations, and that in the long run, it could help to get better technologies.
Oh, for the long run, I think the technology is come to stay. It's just a matter of time that we say, how fast can we bring use cases to business cases now? This is important for the industry. And for computational, you will see in the future, you can calculate systems which are not calculatable up till now, or faster, or even cannot calculate at all. So there will be a big game changer in the future, let's say beyond the 10 years.
You're asking that someone who works on quantum computing for actually more than 15 years. So I worked on quantum computing even before it became cool and before it became this momentum. So I'm kind of used into these, hype cycles that sometimes you work on something everyone is excited about, and at the same time you're also working on something nobody is interested in that. I think the biggest thing what you have to make sure is that we're making progress in the development of the technology, but also in the development of how we're going to use the technology. And then if it may take 5 years or 10 years or 13 years, this is sort of like part of the progress. So I think as long as we're making progress, quantum computing remains an interesting and fascinating technologies. And if there's sometimes more interest in there and then maybe at some point less, that's okay. That's part of doing research.
Yeah, I think one of the major challenges here is that people that are involved with quantum technologies in general don't try to overpromise results too quickly. Because I think there's this tension between getting results quickly and getting appeasing investors, appeasing higher ups, appeasing governmental agencies that do the funding. But on the other hand, I think we have to remain grounded in science and be realistic in the assessments of what quantum technologies can bring and when that can happen.
So there typically are 2 or 3 different categories of people who talk about risk. I think the first category from 10 years ago, my company was actually the first startup in the whole industry, and it was in July of 2014 when we started up in Cambridge in England. I think then there was a very large number of people, academics, who would say it is not possible to compute under the laws of quantum mechanics. And this was a widespread opinion. In fact, many governments and many companies were put off because when they would ask these experts, they would get that feedback. Well, that negativity has virtually disappeared. There's nobody today who thinks that this is intractable or not possible. Then there are 2 other types of risk. One is the risk that we don't have the engineering, i.e. we still have scientific breakthroughs that we need to achieve. I think we're now in the engineering phase. There are certain modalities where we know how to scale. So for example, in trapped ions, this is now self-evident. And then the third kind of risk is more ethical. The democratization of technologies and the lack of access is a big issue. Young people today won't accept what my generation accepted. We do not want vast inequalities of wealth, for example. That risk, I think, is a bigger talking point right now. So those are the three types of risks, and I think the latter one is more relevant.